phi of x inverse, right? But this is also equal to
Are we assuming that x bx is y? Or
phi of I'm just saying. Suppose x has an inverse. Suppose x has an inverse, right?
yeah.
That means that that 1 is equal to x times. I'm omitting the star for a moment.
Oh, and then okay, I see what you're saying.
Then, but this is, we just got done talking about how that's equal to 1 in b,
Yeah.
right?
So it would have to move over.
So that makes this, since this times that is equal to that, it follows that phi of x inverse is equal to phi of x inverse. And of course, it's not enough to have it on, I mean, you can prove it on the left and the right. Like I've done it for this, but of course you can also do for x inverse x.
Yeah.
All right. Now the trichotomy property. Let's talk about that. So I have theorem 4.14. I mess with things. So 4.14. So
Are you saying A is a matrix? Like
yeah, capital A is a matrix.
Okay.
In the regular representation of the algebra with respect to some basis beta. And then either A equals to 0, A is an element of the zero divisors of A, or A is an element of the group of units of the algebra. Now I don't know, again, I've forgotten if my zero divisors, my ZDA allows for A equal to 0. Oh, I've made oh, okay, so my ZDA actually is 0 or x is a zero divisor. My language is x is a zero divisor implies x is non-zero. Okay? So in fact, this language is not necessary. I could just say either x is an element, either A is an element of ZDA, or A is in the group of units. So ZDA, it includes 0 as well as zero divisors. Okay? And so the proof here of this, it's just essentially based on the determinant. All right, so like,
Are we saying beta is the v1, v2, bn?
Beta is the basis for the algebra.
Okay, so it's
Yeah.
arbitrary. Okay.
Good, yeah, whatever. And so note, if the determinant of A is not equal to 0, then A inverse exists. In fact, A inverse, I mean, there's not only does it exist, we actually have a formula for it.
Okay.
A inverse is 1 over the determinant of A times the classical adjoint of the matrix transposed. I mean,
I feel like I learned this. Is this from linear?
maybe, I don't know if he did it or not. Like it may or may not get covered. This formula for the inverse is essentially a corollary to Cramer's rule.
Yeah, I think we have done this.
In a given year of linear algebra, I may or may not actually do it.
I'm pretty sure this was how we found the inverse, because the adjoint matrix is. How did you find the adjoint again?
It's the matrix of cofactors.
Yeah, and that's how you get from expanding through a row, right?
Yeah.
And
well, it's actually the determinant of the submatrix formed by crossing out, like the ijth element of the adjoint is formed by taking the matrix where you crossed out the ij.
It's like the cross product, but any direction, right?
Yeah, I mean a specific instance of this formula would be the 2x2 formula that you know and love.
Yeah, you fought the B and D or B and C.
Yeah, like here, I'll write it out. So if we had like A, B, C, D.
No, yeah, we went over this in linear. It's BC flip negative, right? Or AC flip into negative.
The classical adjoint, like it's the determinant. So like 1, 1, you cross out the first row and first column.
Yeah.
And that just gives you the determinant of D.
Yeah.
But I won't write that again because determinant D is D.
Yeah.
C.
Yeah.
This one, B. And then this one, A, right? So flip the diagonals like that. And oh, I forgot, there's a sign that comes in. There's a plus minus. There's a -1 to the I plus j factor.
Yeah, that's what I was saying. It's kind of like the cross product.
Yeah, kind of. It is, you know.
It's the cross product, but you can expand off any row.
So
he told us you always want to look for zeros.
So then the actual formula for the inverse here is 1 over AD minus BC.
Yep.
Flip the diagonals, but minus negating off the diagonals.
Yep.
Because you still have to transpose.
Yeah.
Transpose to get to that.
Yeah, we went over this. Okay.
But I mean, if you look at my linear notes, I have the formula for the 3x3 inverse in all of its explicit and annoying glory.
Yeah, that's the one we did. Cofactor expansion, yeah. And then,
but of course, the faster way to calculate inverse is just put in a matrix, concatenate with the identity matrix, and row reduce, and all that. But
no, he made us do this.
Oh, okay, interesting. But so yeah, I mean that's fine. Now, okay, so either the determinant is non-zero, right? And it's in the group of units, or else the determinant of A is equal to 0, right? And so this is where I have to rely on some linear algebra that you'll learn from Curtis as you're studying this summer, if you keep going there.
I'm trying to finish it.
Probably not. So there's two different things that we talk about in abstract linear algebra. Well, there's many things, but two particularly interesting polynomials. There's the characteristic polynomial and there's the minimal polynomial for matrix. So the characteristic polynomial of let's say you write its function t, you could write it as the determinant of, let's say, ta.
This is characteristic polynomial.
I'm still doing it wrong. Yeah, t times the identity minus a. Or some people will say it's the determinant of a minus ti. If we do it this way, I kind of like that. This is not what I do in my notes, by the way. I use this convention rather, just to avoid sign errors for students in calculation. The number of minuses you have to put into the equations greatly increased with this convention. But the nice thing about this is if you do this, what this looks like is like t to the n is the nth order coefficient that when you actually expand it, plus stuff, all right? So the characteristic polynomial for A defined in this way, it's going to be monic. It's going to be polynomial with the leading coefficients 1.
Wouldn't you get a... Wait.
This one on the other hand gives you something like -1 to the n.
I was about to say.
T to the n. So not maybe monic. I don't know. It depends on the.
What does monic mean?
Monic means leading coefficients 1.
Okay. Yeah. Wait, don't you have to pull out a negative sign somewhere for that determinant? If you're gonna do that, Should you have a negative on the front of the chart?
This one?
Yeah.
No.
Why are you flipping it?
Because I did a minus ti, this is ti minus a.
So where do you?
These are two, like some people define the characteristic polynomial to be this,
Yeah. Oh.
other
Okay.
people would define the characteristic polynomial to be that. It's choice of convention. Probably Curtis defines it to be the former rather than the latter. And anyway, the larger point here is that the characteristic polynomial of a matrix, n by n matrix, is itself an nth order polynomial. All right? Kayla-Hamilton theorem, what's it say? Kayla-Hamilton theorem is something that often gets stated in undergraduate linear algebra, but it's seldom proved. It says you can evaluate characteristic polynomial with t equals to a, you get 0. So for example, if your characteristic polynomial of a particular matrix works out to like t cubed plus 3t squared minus t, for example, then that means that the matrix cubed plus 3 times the square of the matrix minus the matrix is equal to 0. Actually, to make this more interesting, let me say plus 2. How does the plus 2 appear? When you evaluate this polynomial at the matrix, the 2 has to be understood as 2 times the identity. Otherwise, you can't just add 2 to a matrix, right?
Yeah.
Like this is a sum of products of powers, matrices. This is a matrix plus a matrix plus a matrix. So the 2 has to become a matrix. But in that sense, if you evaluate the polynomial at the matrix, it gets 0. This is the Kayla-Hamilton theorem. It says every matrix satisfies its own characteristic equation in this sense. This is true, but it's actually kind of a deep thing to prove. This comes at the expense of a couple of weeks worth of lemmas and development. It's not. Don't be deceived. You can always deceive students by saying, of course, you just plug a into here, so you've got the determinant of a minus a, which is 0. So yes, that's a good reason, intuition for it to work, but you got to understand that you're actually there's a lot that goes into making that. There is a context in which that calculation can be made rigorous, but it's not what's typically done. My brother said that essentially the details to make that rigorous are in this old book by McCoy, Real Rings and Ideals by McCoy, which is something we might look at later. It's got a lot of good ring theory in it. What we're going to find out once we get further into this is we need more than linear algebra. We actually need to learn how to do linear algebra where we've replaced the field of scalars with a ring of scalars. So that rains on the parade of linear algebra quite a bit.
Yeah, I was about to say you can't. Well, don't rings have to be abelian, or is that not true?
Even if it's just commutative ring, there's still there's a lot of noise. It introduces a lot of static into our usual thinking. You'll see. But so this is the Kayla-Hamilton theorem. So I said there's another polynomial that matters, the minimal polynomial. So definition, the minimal polynomial of A is if it is the mnemonic polynomial of least degree I'll put a t here, such that MA of A equal to 0. let me think of a simple example where I can show you the difference between these things. So if we have A equal to say 3103, then the characteristic polynomial of A is the determinant of t minus 3. Ooh, this isn't going to work. I better get rid of that. I'm going to make that a 0 there.
Okay.
So then this would be
T cubed, or everything minus the t squared.
t.
You need a negative there.
No, just t minus 3 squared. I mean,
Oh yeah, sorry, the zeros in it minus. I did determine it backwards.
That's cool. So this is t squared minus 6t plus 9, right?
Mm-hmm.
There you go. Characteristic polynomial. Like I said, order 2. What's the minimal polynomial here?
1.
No. So I need a monic polynomial of least degree.
Where a equals 0.
I mean, I know Kayla Hamilton says if I plug in this will give me 0 if I plug in the matrix, right?
Yeah. Well, couldn't you build that off of like 1, 0, 0, 1? So it always have to be like t squared or something. Is the lowest polynomial you could get. And then,
Well, it's either got to be order 2 or order 1. Those are like our choices for polynomials, since we know that. I know this is totally new to you, so like you're not tracking quite yet, but this is a quadratic that by Kayla Hamilton, if I plug A into here,
oh, it's gonna equal 0.
I will get 0.
How do you get 0?
Can I find a polynomial of smaller degree, which also works? Like, how can I make this 0 in terms of like a product and subtraction of an identity? How about this? Like, A minus 3 times the identity is what?
A minus 3 times the identity. Oh, it was 0.
It's the 0 matrix, right? So tracking back, what is this? This is the polynomial t minus 3. So like t minus 3, if I plug A into that, it's 0.
Oh, it's the factor.
It is a factor. That's a theorem. Theorem. The minimum polynomial must divide the characteristic polynomial. It's more than that though. In fact, the minimal polynomial has to share all of the same factors as the characteristic polynomial. So like, in fact, the only polynomials to check for this example are the characteristic polynomial itself, there's really nothing to check there, or the factor. There's only one factor here, t minus 3. So like the only other choice besides the characteristic polynomial is t minus 3.
Okay. Wait. So if it doesn't share it, so like if you had 3, 0, 0, 2, it wouldn't. You couldn't have a minimal polynomial.
There is always a minimal polynomial.
What would it be? The
At worst,
characteristic.
At worst, it's the characteristic polynomial. Like if we're working over the reals, this one. So this one here, has characteristic polynomial, t minus 1 squared plus 1, right?
Mm-hmm.
You can't factor that as a real polynomial. So it follows for this one, the characteristic polynomial is the minimal polynomial.
Why would it be t minus 1? Can you do, wouldn't this, so that wouldn't be minus, no, t plus 1, t, okay, I got you now.
If we're working over the reals. Now,
Yeah.
if we're working over the complex numbers, then they're factors. But even though there's factors, actually, remember I just told you there's a theorem that says that the minimal polynomial has to have all the same factors as the characteristic polynomial.
Yeah.
If that theorem is true, if I'm not remembering it wrong, right, and you should check me on it, then this can't be the minimal polynomial because, I mean
It doesn't share factor I.
one of these or the other can't be a minimal polynomial because you need both.
Yeah.
So that means that this matrix is one for which the characteristic polynomial is the minimal polynomial. But you never need to look past that. Like since the Kayla-Hamilton theorem says that when you plug the matrix in, you get 0. That's that's the worst case scenario. Minimal polynomial has order n squared. Order n squared. Yeah. So, but the larger point here is there is a theory of, let me call it polynomial linear algebra. The theory of polynomials for linear algebra, which gives you extra insight into the structure of matrices and how they have to behave. And the way this whole story interacts with eigenvalues is very interesting. I'll just say that. But the larger story here is there is a minimal polynomial for each matrix, all right? And at worst, it has degree n. So what does that have to do? Let's see here. I'm trying to think how this links to the, I need to connect this to the determinant. I'm trying to remember how the
We're talking about the adjoint, then we went over something else.
I mean, this is the determinant right here.
Yeah.
I think, given our conventions, okay, yeah, there's just some, this is not hard out. I'm ready. My mind is clear now. Okay, so let's think about it. Come on. Come on. So in our current case, let me bring us back to here. Determinant 0, right? Notice that the characteristic polynomial of A is t to the n, right? Plus da 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 plus, it turns out, minus 1 to the n determinant of A in our current what's the word here?
Definition?
Yeah. Yes, our current definition. So the characteristic polynomial of the matrix A evaluated at 0, what happens? Any polynomial evaluated at 0, all that survives is the constant term. The constant term here happens to be minus 1 to the n times the determinant of A. And so, what does this mean? This means that since the determinant of A is 0, what's that say? It says that
n has to be rank 0? Or order 0?
Yeah, n has to, it can't have full rank for one thing. N, I don't know if n is fixed, it's 2, 3, 4, whatever. I mean, that's just, it's either plus or minus 1. So this is plus or minus 1 times 0, which is 0, right? So
oh, yeah, you're right, sorry.
You're fine. The characteristic polynomial evaluated at 0, 0. What that means,
The determinant 0.
well, yes, the determinant 0, but that means that the characteristic polynomial has no constant term.
Okay.
So, I mean, we could write it out. Characteristic polynomial of A.
Oh, so it'd be like,
Yeah.
no.
T to the n plus c n minus 1, t to the n minus 1, you know?
Yeah. Okay, yeah, it'd be like t times t minus 1.
C1, I guess, the counting. C1t, and then like C0. If this was, in this labeling, this would be C0, you know? So the constant term is gone, right? But notice that means we can factor out t.
Yeah, that's it, yeah.
So in summary, we find that t is factor of the characteristic polynomial of the matrix. But by the theory of abstract linear algebra, we also know that T is a factor of the minimal polynomial of the matrix. The reason that the minimal polynomial is important to us here is because we're working towards finding a matrix which, when we multiply by A, we get 0, and yet that matrix that we're multiplying is not itself 0. If I work for the characteristic polynomial, I have to worry about the whole thing actually just being 0. You can, so like the matrix I had as an example, it was t minus 3i squared, right? So it's like t minus 3i times t minus 3i is equal to 0, but when you actually plug in a into the t minus 3i, it's 0.
Yeah.
So like at the level of matrices, that's 0 times 0 equals 0, which is true, but not what we're looking for. Like I'm trying to find the non-zero thing.
Yeah.
When multiplied by 8 gives you 0. The minimal polynomial is going to do that for us because let's say that the MAT is like t to the, now not necessarily n, let's say r, right, and then b r minus 1, t to the r minus 1, you know, b1 t. I know I don't need b0 because I know t is a factor, right? I probably don't have quite all these details in my paper, right? I don't think I do. I assume the paper is written with the assumption that like a student has studied linear algebra at a somewhat advanced level. So, okay. Which, by the way, has been enough for it to be summarily rejected by various journals. They're like, this is not research level. So like, it's beyond the standard course, right? But it's not confusing enough to be a proper research article. Anyway, so my point to you here is, we can factor t out, right?
Yeah.
My claim is that this matrix, let me call this polynomial, I'll call it,
So you said t is
G-
not 0, right?
GAMT. What's up?
Well, if we know t, and we characterize t as non-zero, wouldn't that have to be something that equals to 0? Like one of those has to equal to 0?
I mean, they're polynomials, they don't have to be 0. They're expressions, I don't know.
Well, I thought t was a matrix.
No, t's is an indeterminate.
Is it?
Okay. It's just a variable if you like, but how about this? Could GA of A be 0?
No, it's a constant term.
Well, but the constant term, that's not a reason why. I mean, that we had t squared minus 6t,
Oh, yeah.
t squared minus 6t plus 9, right? We plugged in a into that, we got 0, that was non-zero.
No, yeah.
The reason is it's more like a logical problem. Remember, MA is the minimal polynomial. It's the polynomial of least degree that when I plug in A, I get 0.
Yeah.
If I could plug in A into G sub A and get 0, that would give me a polynomial of degree r minus 1, which when I evaluate A, I get 0. That would contradict M sub A of T being the minimal polynomial of A, so we can't have that. So it must be, so no. G of A has to be non-zero.
Yeah, because the only way you could get it if MA of t was 0, or t was 0.
Right.
If t is 0, you can have g of a not be 0.
Well, MA of A is 0 by assumption, because
Yeah.
MA is the minimal polynomial. So like it is the case that A to the R plus b.r. to minus 1 times a to the r minus 1, da 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 da.
Yeah.
So in other words, we do know that a times a to the r minus 1 plus br minus 1, a to the r minus 2 plus da 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 plus b1. Remember, we're evaluating at the matrix, so we put the identity matrix on the constant term, right?
Yeah.
So we know this is equal to 0 because of the definition of m sub a.
Yeah, but what I was saying is if A is a 0 matrix, that means G of A wouldn't have to be 0. But
That's true, yeah.
it would give us a result that's kind of boring.
G sub a of the 0 matrix would give us b1 times identity.
Yeah.
That's true. But check out what we have here. So using this minimum polynomial and this string of logic that we've gone through, is this your water?
No.
Okay. So, check it out, right? We've got A. And by the way, I would assume A is non-zero in this discussion. If A is 0, then fine. It's in ZA anyway, we're fine. But note, we've got a non-zero matrix A times a non-zero matrix GA sub of A equal to 0. What's this mean? This means
Zero
this.
factor.
Exactly. A has a 0 vector. It's cofactor. I'll call this GA the cofactor. Or sometimes I'll call it the null cofactor.
Yeah, but if you assume A is not equal to 0, that means that would have, okay, yeah, we're assuming. If
Or
A is not equal to 0.
sometimes I will call it the null factor or I don't know. I need a good name for these things. But anyway, the point is, this tells us that A is an element of ZA. So there you go. But but the beautiful thing about this argument is it's just pure linear algebra. It has no regard to our choice of algebras. This works for the hyperbolic numbers, the three hyperbolic numbers, all kinds of examples we haven't looked at yet, so forth and so on. It's quite nice. And you're like, well, okay, well, this is just for the matrix representation of the algebra. But this theorem over here we have about isomorphism, one of the things is it transfers zero divisors. So if we just combine this theorem and that theorem, it tells us for an associative real algebra, there are just two kinds of elements. There are the elements which are in the group of units, and they are the elements which are in zero divisors of A, which themselves are either 0.
So you can't have okay, so, I mean, then you can make another theorem saying that if two algebras are isomorphic, they have the same amount of zero divisors, right?
That's right. Yes. And the structure of the zero divisors is subsets shared.
Yeah.
And this says more than that, though. This says we can calculate where the zero divisors are by simply looking at the regular representation and looking at the determinant of the regular representation of an arbitrary element. Where those are 0, those are places where we could have zero divisors. And I showed you that a little bit, I think, for the hyperbolic numbers last time.
Yeah.
I saw that, like,
the x, the zeros were on the
y
45-degree angles.
plus or minus x, the light cone, if you will, where the zero divisors are for the hyperbolic numbers. So, yeah. Because, I have hit this question in a more abstract way without using the regular representation, and this question can actually become a lot more difficult if you're not versed in these bits of linear algebra. But with these bits of linear algebra, it becomes, pretty straightforward. I have some other theorems, which I should share with you before we go cook the hamburgers. And it falls on us to make lunch. But you do hamburgers?
I'm not vegan.
Okay.
That's what you're asking.
Yeah, that's good. I'd have to kick you out of my house.
I was vegetarian for like 6 months, and then I was like, chicken nuggets sound really good, and that was the end of that.
Wow, so you were chicken nuggets brought you back?
Oh yeah.
Wow. But you're not old enough for them to be the dark meat nuggets either, so.
Hang on, chicken nuggets are good.
Yeah,
I sound like a 5-year-old, but it's fun.
But you're not wrong there. They're actually quite good. Curses, I lost my page. All right.
That's what I would do after class. And when we get out like at 9, I'm like, let me get some chicken nuggets.
Okay, so one theorem that I think I like more than anybody else, but I just think it's cool, is that the zero divisors of A are closed under negation. So like zero divisors of A, it's not a subspace, but it does end up being kind of like a union of subspaces. So it's an interesting kind of space. It doesn't really fit into linear algebra, the zero divisors of an algebra. Let me show you what I'm talking about. Now you can already kind of see what I'm talking about if you think about what I showed you for the hyperbolic numbers. What are the zero divisors?
What was it? I gotta think for a second. So j squared was equal to 1, right?
Mm-hmm.
So whenever x and y were the same number, so everywhere that x and y were equal to each other.
Right. Yeah. Either y equals x or y equals minus x. Those
Yeah.
are the lines through the origin
Mhm.
of slope plus or minus 1, if you
Yeah.
like. So my point to you is, if you take both of those together, is that a vector space? Well, is that a subspace of R2? Well, I mean, no. Right? It's a union of two subspaces.
Yeah.
But for higher dimensional algebras, it ends up not just being a union of equal dimensional subspaces. It can be stuff like a plane union with a line.
Oh.
There's all kinds of like
Oh yeah, that makes.
other possibilities in higher dimensions for what the set of zero divisors looks like. But the larger point, though, is just this: the zero divisors, they do appear as the solution set to the characteristic polynomial equal to 0. I mean, they have to be in there because minimal polynomial and the characteristic polynomial share the same factors. So we can find where the zero divisors are by looking at the determinant of the regular representation of an arbitrary element equal to 0. That will reveal to us where the zero divisors are in the algebra. But I would point out that it's necessarily smaller dimension than the algebra. Like the zero divisors can be, if the algebra is 3-dimensional, you could have 1-dimensional or 2-dimensional.
Oh, okay. I thought
Zero
you were saying. I
divisors.
was about to say. I was like, if you're saying it's a 3-dimensional, that means the whole thing could be a zero divisor.
Yeah, that doesn't happen.
Yeah.
Unless it's just,
The entire algebra would have to be zero divisors.
So yeah, I mean, there was always this stupid zero algebra where you define the product of any two things in the set is 0. You pick the thing in the set which is, and like...
But that would mean J or whatever you use would be 0.
Yeah, I think there, if we do that though, I think we don't get unity. So I think that's like outside our definition because it wouldn't be unitable. But I don't know.
You also have one unique inverse.
There's a whole discussion about what happens when 0 is equal to 1 in a ring and how to understand that, and I frankly don't care. So I'm a bad math professor. Okay, so getting to the point, there was a point here. The zero divisor of A is fixed under negation, and by what I mean by that is if X is an element of ZA, then in fact it's I mean in negation, but you could in fact say scaling. So this multiplication by C, right? C equals, this is just C equals minus 1, right? So if X is an element of ZX, then that means what? That means that there exists y not equal to 0 such that what? X times y equals to 0, right? But Cx times y is equal to C times X times y, right? Which is equal to C times 0, which is 0 again. And the juxtaposition here is multiplication in the vector space, whereas the star is multiplication in the algebra. But as you can see, Cx is an element of ZA. So like whatever these sets of zero divisors are, if you've got one, then you can just keep going. So like there's always a line through the origin of any one that you find. So they have to appear in subspaces, but it may or may not be the case that you can find a basis. In fact, I think usually, I don't know of an algebra where the zero divisors, like all of the zero divisors for the algebra forms a subspace. I'm actually not aware of an example where the zero divisors of the algebra form a subspace. They're always like a union of subspaces.
I was about to say, you'd have to restrict it.
Yeah. Now, so that's one thing. It's kind of nice. Another thing is that theorem in this I oscillate between this theorem being obvious and this theorem being really hard to understand. So theorem, there exists an invertible basis of A.
Yeah, you lost me. How is a basis invertible? How is a building block invertible?
Well, this is an algebra, so every element is either invertible or not.
Invertible on a mapping?
Invertible as an algebra element.
Oh, yeah, I'm lost.
So here's an example. An example of a non-invertible basis. All right, hyperbolic numbers, right?
Yeah.
It is the span of 1 plus j and 1 minus j.
Mm-hmm.
So as in here, of course, we're working with R2, and so that is the vector 1, 1. This is the vector 1 minus 1, right?
Yep.
Those are a basis for R2. They're linearly independent, but this is very much not an invertible basis, right? Because both 1 plus and minus j, they're all elements of the zero divisors of the hyperbolic numbers. So this is an example of a basis which is not invertible, but my theorem says that there exists an invertible basis. And of course, it's easy to find those, right? I mean, like, what's an invertible basis for the hyperbolic numbers? 1j is an invertible basis because 1 times 1 is 1, and j times j is 1, right? So in fact, j inverse is equal to j, which of course is an element of the group of units for the hyperbolic numbers.
So if we have a basis 1j, we're plugging 1j into... Oh, we got 50%.
Yeah, let me draw a picture.
Yeah, because are you saying... Because our regular basis is non-invertible, but if we change our basis to...
Oh, I think the usual choice of basis is invertible. This weird choice, you might call it a light cone basis, it is degenerate in the sense that, I mean, it's a non-invertible basis.
Yeah.
Because and by non-invertible, I just mean that the elements in the set themselves are not
But you can...
invertible.
Okay. Oh, I'm with you now.
Alright, so like this basis pictorially is 1 plus j, so it's like here and here, 1 plus j, 1 minus j, right? So it's like this guy, and this guy, you know? And I mean, clearly those are not linearly dependent. So this theorem, and this is a true theorem, but proof of it, I mean, proof of it requires I would say somewhat of a leap, depending on your background. I think it's actually intuitively clear once I point out to you what the argument is. So like, you take a basis. So to prove that there exists an invertible basis, right? Take a basis, all right? And, you know, proof goes something like this. Let beta v1, v2, let vn be basis. All right? Of course, if these are all invertible, we're done. Okay, so suppose, without loss of generality, that v1 inverse does not exist. All right, so if needed, reorder them. So the first basis element is the non-invertible one, right?
I'm just doing stuff for my head with the non-invertible one. y1, and that would be minus 9. Why is it the top one? Yeah, now why is it the top one invertible? Because 1 minus j times itself would be 1.
Oh, why is 1 minus j not invertible? Because the product of those two things is 0, even though they're not 0. 1 plus j times 1 minus j.
Oh, okay, the product of them together, okay.
And so those two things are zero divisors, and zero divisors are not units. These are disjoint categories.
Yeah. Okay, so.
Yeah.
So suppose. What is after suppose?
Without loss of generality, v1 inverse does not exist. If needed, relabel them. So the first one is the one which fails to have an inverse. All right.
So that'd be like the identity? The identity has an inverse too.
No, I don't know what v1 is. It doesn't have to be the identity. It could be the, in my example, it could be the 1, 1.
Okay. I'm going to use zero divisor. Okay.
So here's the thing. The zero divisors are a space of lesser dimension in n dimensions. But another way to phrase this is the group of units is dense in the space. So AX is dense in A. Because I mean, if you think of AX as a manifold, its dimension is n.
Yeah.
It's basically formed from taking the algebra and deleting some subspaces of dimension less than the whole dimension of the algebra. So like AX in the hyperbolics it's the union of those 4 wedges. HX, the group of units of the hyperbolic numbers, for example, it's those 4 disjoint regions bounded by y equals plus or minus x, right? So like this is hx1, maybe hx2, hx1, hx3, hx4, hx is the union of these guys, right?
Mm-hmm.
Now, what does it mean for a set to be dense in another set? Did you talk about this in reals?
No.
Like the rational numbers are dense subset of the reals. The irrational numbers are a dense subset of the reals.
I feel like I don't know if this has anything to do with it, but I feel like it goes along the lines. He was talking to me, but this was like outside of class. He was talking to me about how what do you say? Has like essentially like if you take the set of real numbers and delete all the rational numbers, you still have like an infinitesimally large set.
Yeah, infinitely large, yeah.
And that has some degree. That means it's like it always will be. You can take out something and it's still infinite. It has something.
Yeah, it's beyond countably infinite. It's larger than the natural numbers.
He was, I forgot what he said specifically, but like there's an order or a rank or something like it. It means like even if you took a whole subset out of it, it would still be infinite. Like it's
it has like that. The reals with the rationals deleted, the irrational numbers as it's called, has the same cardinality as the real numbers itself.
Yeah.
Because rationals, despite the fact that they're dense in the real numbers, they're a countably infinite set.
Yeah.
Meaning that they are in one-to-one bijection with the integers. Because you can take the rational numbers and
map it as A over B.
Right, put it in these terms, and then you can make a zigzag path through the integer lattice of like rational numbers of the release representation. This mapping was constructed, I think, first by Piano.
Yeah.
And so that gives you this one-to-one bijection between the rational numbers and the integers, which means that it has the same size.
Yeah. So is that what this is saying?
No.
So
I mean, it's a related discussion perhaps, but dense just means that if, so here, by dense, in, like dense is a concept of topology or perhaps analysis. Topology is abstract analysis, but basically if your subset is dense, you take a point in the dense subset. If you take an open set around that dense set, then no matter there are infinitely many points not in the set which are not in that dense subset. I think is one definition for it. Now I'm not.
Oh, okay. This is.
Tell you what. Give me a second here. Let me look up the correct Wikipedia definition for us. So
I kind of get it though. It's like the same thing that I was trying to say. Like you can. There's enough points where even if you took them out, you would still get a infinitely big set.
Yeah, let's see here. Here's what Wikipedia tells us. He says in a topological space X, a subset A of X is dense if every point in X either belongs to A or is a limit point of A. And what's a limit point? In other words, the closure of A constitutes the whole set. So informally, every point in X is either in A or it's arbitrarily close to a member of A. That's the sense in which I've been using it here in the informal sense. But we could be more formal, dense in the sense of metric topology. We're in Rn, we can use Euclidean topology in the sense that we're defining distance between points by the square root of, well, excuse me, we're not in Rn, we're in an n-dimensional vector space. But in an n-dimensional vector space, we can take a given basis and we can build a norm from that and define distances accordingly.
So AX is all the numbers that are invertible, right?
Right.
And so it's dense because all the numbers that are invertible also over.
It's now in contrast, zero divisors are not dense. All right.
Yeah.
Because there are definitely points in my example, like points over here are nowhere near.
Yeah.
Points outside of the group of the points in here are nowhere near the zero divisors. These are not limit points of the zero. Limit points.
Yeah. So like essentially like any constant of j, or j times any constant.
Yeah, the limit points. Well, the limit points of the zero divisors are the zero divisors because the limit points, because the zero divisors, and again, everything I'm saying is with respect to the standard Euclidean topology of R2 for my hyperbolic number example. But the zero divisors of hyperbolic numbers, the lines y equals plus or minus x, these are in fact a closed subset.
Okay.
And the closure of a closed subset is the set itself, and but the limit points of a closed set are points inside the set. You know.
And why is it closed?
Why is it closed? Because it's complementable. So the complement of the zero divisors
h of x, right?
is like hx, right? Which is, it's got fuzzy edges essentially. Like, pick any point outside the black lines, you take a point, you can find a disk around that point which is inside that set.
Yeah.
And inside, like, the group of units. The group of units is open. Another argument is that hx is the inverse image under the determinate mapping of, oh well, I'm borrowing from a few things there, but it is essentially the inverse image of the non-zero real numbers, which themselves is an open set, and so it's the inverse image of a open set under a continuous map, which is again open. But to do the work there, I'd have to explain to you why the mapping I'm thinking of is a continuous map, and
I'm kind of getting it though. Yeah. So if I pick a point,
I probably should just.
if I pick a point in hx, I can get there's enough points around it to where there will be a subset of h.
hx, but yeah.
A subset of hx.
So that's what it takes for hx to be open, is for each point in hx to be interior.
Okay.
So, okay, so getting back to the original theorem. The argument is just this, like, okay, so V1 inverse doesn't exist, right?
Yeah.
Fine. But the group of units is dense, which means that there is some element as close as you like to V1
That is invertible.
that is invertible, right?
Mm-hmm.
And then the argument is if it's as close as you like to V1,
It's just v1.
that should mean that if you replace V1 with that invertible element, it shouldn't spoil the fact that it's a basis. If it does spoil the fact that it's a basis, you had the misfortune of having something else in the basis which is very close to V1. But because the density allows you to pick it as close as you want, you then just say, okay, well fine, I will make it even closer.
So like if for some reason like the